Okay guys, so in this video I'm gonna review a very fast complex integration. So first of all, you know, our function is a function of a complex variable. Okay? So we need to define what is a function to be analytic. Analytic is the closest thing to be the function to be differential. Okay, so we don't say f is differentiable, we said f is analytic. And you had seen many, I request people to talk about Taylor's theorem and power series, right? So, well, f is analytic at C0, that is a complex number, if there exists a power series of this form. Okay, C equals A plus AB, A, B are real numbers. And this is a power series, and this series it has some radius of convergence. Okay, and the convergence is absolutely. Okay, so this is around a radius of convergence, and then we said that the functions can be written in this form. Okay, so a function is analytic. Basically, you can write it in this form. This is basically, it has a, it looks like a power series development. Okay, I following the complex analysis by Serge Lang. Okay, you will see there very nice presentation. So yeah, so if f of c looks this way, uh, if f of c has further a representation from minus infinity to infinity, that means, you know, if you start, if n is a0, so you start a0, then a1, a2, right, a3, etc. But then you have also the negative numbers, so you have minus 1, n can be minus 1, so you have a minus 1, 1 over c minus c0, plus a2, 1 over c minus c0 squared, and so on. Okay, so this is called the this is the Lorentz series representation at the point c0, and we call a minus 1 the residue of f at c0, and write it this form. So really, this a minus 1 is going to be fundamental for us. That's how you're going to calculate the residue, the integrals. Okay, we're going to calculate integrals using this guy, that tiny little guy, fundamental in this theorem. So then we have the residue theorem. So you all, I think you all supposed to have a complex variable class. Okay, so all of you supposed to did some complex integration when in your undergraduate. And so this is more like a review. So let C0 be an isolated singularity. That means division by 0. Okay, so and this is really what we are talking about here. Okay, so if you don't have singularities, you don't have division by 0, well, your integration is gonna be look very nice. I'm gonna do an example here with the integration. You don't have singularities, your integration, if you can apply fundamental theorem of calculus, just looks like calculus. Okay, we'll do that example at the end. But this one is this residue theorem is for when you have singularities, division by 0. For example, find the integral of 1 over c minus c0 dz. Okay, so we have a singularity at c0. So that's kind of the function we're looking at, the difficult integrals. Okay, so let's see 0 be an isolated singularity, just like the one I did, of f, and let's see be a small circle oriented counterwise centered at c0. So it's a circle and it's counterwise, such that f is holomorphic on c. So holomorphic and analytic is basically the same thing. Okay, so I'm gonna call it holomorphic, I'm gonna call it analytic. Holomorphic means really that those singularities are kind of you can work with those singularities. Okay, so I'm not gonna go into that, but holomorphic and analytic, you can play with those. If you are careful, just the one replace the other one. Okay. So it's holomorphic on C as at its interior, except possibly at C0. So it's saying it's analytic, maybe except at C0. So you're having an isolated singularity. So what it says here is the integral of the function around the curve, okay, equals 2 pi I a minus 1. So this a minus 1 that we were talking about, the Lorentz series representation. And this is a minus 1, we just said we will use this funny notation, residue, okay? And then what does it mean holomorphic? F is holomorphic only if F is analytic, that's true. But holomorphic means that you can really play with this singularity C minus theta 0 times F, that limit will exist, okay? So that means holomorphic allows you to play with that singularity with this trick, okay? So it's gonna be, but you know, you have to read about it. I don't wanna make it sound simplistic, but yeah, I mean, for engineers, holomorphic analytic is the same thing. For you guys, you should probably go further and read about it. So finally, why do I need this? Because I'm gonna talk about Fourier transform. So Fourier transform is a complex integral, it's not a real integral. And this theorem is in the book of Serge Lang. By the way, another famous book by John Conway, I like that book better than this one, but it's more mathematical. But John Conway just passed away recently, and he did complex analysis. It's a very famous book. Okay, I never had the chance to ask him to sign the book for me, but a friend did. So he passed away recently. So this is also honoring him. John Conway. Let me look for you, John Conway. He just passed away. And he has a beautiful book in complex analysis. That's the book that I follow in my graduate studies. So you can read about him. Okay. So sorry for the going away. So this is the Fourier transform. So let F be meromorphic or analytic is on complex, having only finite number of poles. That means singularities. So no line on the real axis. So let me see if here is this is F, and these are singularities. But you see, you can make them around circles because they are separated because you have a finite number. Suppose that X is a constant case such that the function can be bounded like this. Because this is fundamental. Your function just cannot be any function. It's like Laplace transform has to be bounded by a exponential thing. This Fourier transform has to be, the function has to be bounded by this guy, with this kind of thing. Okay. So for all sufficiently large C, okay, let A bigger than 0. Then you see this is my Fourier transform. The Fourier transform of F. Well, this is really inverse Fourier transform, right? Well, it doesn't make a difference, right? For us, A can be, will apply. So this is gonna be 2 pi I plus the residues of e to the I ACFC in the upper half of the plane. So to find the Fourier transform of this F, you have to find the residues of the upper half, and then but the residues, how do you find the residues? That should be part of the video, but I don't want to make it more complicated. The residues, you found the residues with some tricks, with some formulas, finding limits. But basically what you need to do is find A inverse. So you know A minus 1. If you know the Lorentz development of the function, then you can find A minus 1. Okay. I don't want to, this is a whole semester class, so I don't want to I wanna try to help your memory, okay? So you can go to your notes, but let's not not everything is complicated. So let's take the Fourier transform of this simple function. So this is 1 over here and 0 other between minus a and a is 1 and otherwise is 0. When you take the Fourier transform, look at this. You see this is just a signal, right? This is a pulse, right? So you this is a pulse, you push the click and then look at how beautiful transform become a signal when you apply the Fourier transform. So how do we apply this? So with the Fourier transform of xax, but xax is just 1 between minus aa. So I apply this to the fundamental theorem of calculus, and I got that, right? And then I plug in a and a minus a, and then apply my Euler formula, and then they simplify, and finally got that 1 over square root 2 pi 2 sine theta a theta is my solution, the Fourier transform of this one, and the graph is this one. Okay, so that's how you find. If you don't have singularities, it's beautiful. This fundamental theorem calculus is what you do, but if you have singularities, you have to use this. You have to use this formula, this theorem. That's the way. How do you have those formulas? Remember, I showed you this formula. You have to prove it. Example of here equation. Let's see. No, this is not. We have a formula when we're proving the Fourier transform of. Let's see this one. No. I'm sorry, I'm trying to find my heat equation formula. Remember, in the heat equation for the whole real line, we had to use a formula, but I don't see it. No, sorry, I don't see it here. Yeah, okay, so let me check, let me find it here. In the note, if we go to announcements, I'm gonna show you here so any formula you use is proven in that way. Okay, sorry, course materials. So for example, this formula from homework 7, this formula is proven using this kind of stuff. Okay, the Fourier inverse of this is that. So you will have to use residue theorems to solve it. Okay. Clearly you see that this integral will be hard to solve, like real integration. So you have to do complex and then you solve it. Okay, so we think we can stop.